Okay, so hi everyone. Welcome to my talk. So I'm Jackson Lee, working mainly on computational morphology, working with John Goldsmith at U Chicago. So today I'll be talking about algorithmic approaches to identifying inflectional stems. So first of all, I'd like to give you a flavor of what interests me in general, a big picture kind of view. So in general, I'm interested in patterns in morphological paradigms. So by paradigms, I mean, for example, in English, we can talk about jump, jumps, jumps, jumping being a paradigm, so the jump paradigm. And then another paradigm is like find, finds, found, finding, and et cetera, et cetera. So my central interest is pretty much two things. So one is about structure across paradigms. So for instance, when we talk about inflectional morphology, we observe patterns like inflectional classes, stem alternations, or allomorphy, and so on. Another thing is structure within a paradigm. So given a paradigm, what is really robustly observed is that, for example, given the jump paradigm, we see that there's some material that is shared across all the forms in a given particular paradigm. So the specific question that I want to ask today and to answer to some extent is this one. So given a morphological paradigm with inflected words, how exactly do we know what the stem is? So if you think about the way we do linguistics, for example, in Linguistics 101 or in any introductory morphology class, when you're given some data set and you have morphological analysis, the one thing that you had to do, first thing perhaps, is, for example, let's say you don't know English, and then you're given this, and then you're told that this is a paradigm. This is a paradigm, and you're asked to do some analysis. Without any further information, without prior knowledge of the language, without meaning whatsoever, the best that you can say is, oh, we observe that these four words kind of share this common material, which we might call the root material or the stem material. So that's the intuition. Sounds like something basic, but then if we look at the literature, like the computational people like John Goldsmith himself, and also some review papers in the leading journal in computational linguistics, we see people still talking about pretty much the basic problems in morphological analysis, and that is segmentation, morphological boundary discovery kind of problems. Outside computational world, if we look through the recent papers, we see that people like Andrew Spencer are still talking about, hey, how do we identify a stem given a paradigm? Is that really that trivial? Is it really that basic? Is it really something that we have kind of taken for granted? So by that, before I dive into my solutions, the meat of the talk, I'd like to say that, so for any solution that we want to come up with, we would like them to be, first of all, algorithmic, which basically says that we want it to be pretty much like a computer program. It's a procedure, like with steps, like clear, explicit steps. Given a paradigm, here's a program, it should output some analysis. So that's the meaning of algorithmic. It's in the computer science sense. Another thing is that we would like the solution to be language independent. So regardless of the language, without any prior knowledge of the language or languages, it should give us some analysis, some insights about the language or the given data. So as always, when we talk about computational morphology, pretty much the kind of stress test, the stress case is Arabic, for example, because of the famous root and the consonantal root patterns. So for example, as is well known for Arabic, we know the consonant root KTB has something to do with writing, to write. So here is a part of the paradigm for the related words. So he wrote, we wrote, and so on. And they all have this, the KTB pattern, like interspersed with some vowels and other things here. So now the problem is, for English, for something completely concatenated like the jump paradigm, it seems intuitive and kind of quote-unquote easy to pull out the stem material. But then if you look at things like Arabic here, okay, in any intro linguistics, we will tell students that, wow, it looks cool. It's wildly different on the surface, at least. Are they really fundamentally that different? And today, I would want to say maybe formally no, and you will see how things work here. So Okay, back to Andrew Spencer's paper. All else being equal, he says a stem for a given paradigm is the maximal common material across all the word forms, which is intuitive. That's that's the best that we can say, right? I mean, without any prior information, no fancy math whatsoever, that is the best that we can do. So by this, what we mean is something like this. For example, given a jump paradigm, you don't want to say the stem is just the string JUM, because you can still pull out the P here as part of the common material, right? So that's the basic intuition. But then today I'm gonna say we shouldn't be happy with this idea. I mean, it's good, but then we shouldn't be happy, because we can still push it further to formally specify what exactly we mean by maximal common material of a paradigm. So before I get into the various ways of understanding this, I'd like to bring in two concepts here when we try to talk about strings here. So the two concepts are linear ordering and adjacency. So let's now consider an arbitrary string like A, B, C, D, E, 5 symbols strung in this way, in this particular way. So by linear ordering, we mean, for example, A precedes B, and also A precedes C. By precedes, we mean A comes before C. So that's the intuitive idea about the linear ordering relationship. As opposed to, for example, D does not precede C. So given this arbitrary string. The second thing is about adjacency. For example, we say, given this string A, B, C, D, E, A and B are adjacent to one another. Other examples being, for example, B is also adjacent to A, despite the way I said it, to say this kind of adjacency relationship. Other examples include B and C being adjacent to each other. But then when we talk about A and C, for example, they are not adjacent. So two ideas here when we talk about strings, crucial for today's talk: linear ordering and adjacency. Okay, back to this intuitive idea spelled out clearly from Andrew Spencer. So stem is the maximal common material across all the word forms. The way we try to formalize this is as follows. We find that there are three natural ways. Natural ways from well-defined ways from mathematics and bioinformatics, such as DNA sequencing kind of work. So the three ideas are here. So when we say maximal common material being the same, we can mean the substring, maximal common substring, maximal common multiset, or maximal common subsequence. These are all technical terms to be defined using the ideas of linear ordering and adjacency. So before I get into the three solutions, I'll be using these Spanish paradigms a lot. So Spanish, like other Romance languages, have basically three major conjugation groups. So for Spanish, we talk about ER group. I'll be using poder to be able to, or can, a lot. So for the present indicative conjugation, as is well known, we have puedo, puedes, puede, podemos, podéis, and pueden. So what we notice is that, first of all, the affixes, for those of you who don't know Spanish, you will know that for the ER conjugation, the affixes are always like this, like o, s, e, hemos, es, en. But then what is special for this verb is that there is what people have called stem changing the character, right? So puede, sometimes it's puede, sometimes it's bod. So this kind of, in a sense, it's kind of like Arabic case. It's like it's not exactly concatenative. Something is changing, like spanning across the stem, as opposed to, for example, if you look at comer, to eat, so como, comes, come, comemos, coméis, comen, exactly same set of affixes, but then the stem doesn't alternate. So that's the contrast here. So take this one as a jump paradigm in English, for example, concatenative. Okay, so first idea. When we want to say the stem being the longest common substring of a paradigm, we mean, so substring being linear ordering has to be observed, adjacency has to be observed as well. So by that we mean, for example, given some arbitrary string A, B, C, E, for example, legal substrings are or include A, B, B, C, A, B, C, and so on and so forth. Illegal substrings are things like BA, because it violates linear ordering. AC is not good either because it violates adjacency. So very basic ideas. Now, when we asked a computer program, hey, now I give you the Goldsmith paradigm, Gomo, Gomez, Gomez, and so on. What is the longest common substring? Because I take that as a stem. The answer turns out to be COM. Good news. It's like the jump paradigm, JUMP being the stem, according to the substring analysis. But then, as we know, this first approach works well because of the completely concatenative character of this paradigm. So the problem is here, when we look at anything that deviates from strict concatenation, we see problems with the substring approach. So we ask the same question, hey, what is the longest common substring as a stem when we look at the Baudelaire paradigm, these 6 words here? It turns out that there are 3 competing analyses here, and they are P, just a little p, that's it, just an E, that's it, and just a D. All of them are no good because intuitively for Baudelaire, we want to say both P and D are part of the stem material because P and D are the lexically specific material for Baudelaire. The E it's a kind of an issue here because E is sometimes part of the or where vowel alternation. Sometimes it's part of the affixal material. So it's the issue here in the substring approach. So we need something better. So I take this substring approach as the most intuitive idea when we don't think about strings too deeply, because we always take linear ordering and adjacency for granted. So now we are basically playing with these 2 parameters. Okay, second approach. Let's not talk about substring. Now we talk about a stem being the largest common multiset. What is a multiset? So let's talk about set in the mathematical sense. So a set is a bunch of objects, but then we don't allow repeated elements here. When we say multiset, we allow repeated elements. So that's the meaning of multiset. So in particular here, multisets don't obey linear ordering, and they don't obey adjacency altogether. So we throw away the 2 parameters here. Basically, a string is formally a bag of symbols. So that's the meaning here. So for that, what's the result here? Aha. So given these 6 words, a computer program would say, hey, P, they all share 3 symbols, and they are P, D, and E. That's better. We have P, D together, but then we still have the E problem here because not observing linear ordering makes us unable to see whether E is part of the or-where alternation or whether it's part of the affixal material. So something is still missing. It's no good. So let's adjust the analysis a little bit, and now we come to the third approach, which is the subsequence approach, widely used in DNA sequencing in computational biology. So now if we say that stem is the longest common subsequence, what we mean is that it's kind of like the substring approach, but then we don't necessarily obey the adjacency requirement. We could, but then we don't have to necessarily. So when we try the Baudelaire paradigm with this approach, the subsequence approach, we find this. There are 2 competing analyses here for stem analysis. So the first one says P and D, the subsequence P and D. The second one is P and E. So intuitively, we want to say PD being better than P because now the game that I'm playing now is that we look at paradigms one at a time. We have no information about other paradigms in the language. So down the road in my work, when I look at paradigms en masse, like putting a bunch of paradigms together in a program, in a system, intuitively, this should be chosen to be superior than this analysis because we can see the affixes like O, S, E, Emos, A's, and like picked out, which match better with the affixes from other paradigms like omena and other ER verbs in Spanish. So that's the intuition about what I'm trying to do. Okay, so to give you the kind of the concluding remarks here. So within paradigm, looking at paradigms one at a time with no information like frequency and whatnot, no prior information about our language or languages in question, the best that we can say about the stem is, as we claim, it's the longest common subsequence. That is, we still care about the linear ordering, but then we don't necessarily care about adjacency relationship. So that's the major claim here. And we find that this approach works well for a wide variety of languages with different morphological types. So English, Arabic, Spanish, etc. And I'll be showing you like more data, more examples when I show you a little computer program that I've written. So next is about across paradigms. So as I said, for the Baudelaire problem, we say that, well, P and D are part of the stem intuitively, but then we still have the all-way alternation, for example. And then you might wonder, is that? So does my analysis say that it's not part of the stem? Well, not quite. If you look at cross-paradigmatic kind of comparison, we need other paradigms together. And then you can say that, oh, we see the all-way alternation is recurrent in a lot of paradigms. So, and then that's how we learn the morphophonology in Spanish and other Romance languages. Another thing is, of course, about the inflectional classes. So by pulling out the stem, what is left is the affixal material intuitively. So we see the O, S, and so on, the affixes. When we put a lot of paradigms together, we can see some differentiation of inflectional classes like the AR verbs, IR verbs, and ER verbs in Spanish, for example. So beyond this kind of specific material about the talk, we would like to basically to be clear about what we do what we mean by doing linguistics. So pretty much what we do is in line with what Z.A. Harris has said in the structuralist tradition. So basically, doing linguistics, it's about coming up with methods or algorithms that can be applied to languages without any prior knowledge of the language or languages in concern, and then we learn the structure about the languages in question. Another thing is about philosophical point about research. So we would like our research to be reproducible in the scientific sense, accessible. That is, we want our tools, our fancy stuff, to be usable by other people in an easy way. The third is about the extensibility of our research. Here it means, for example, two things actually. One is the cross-linguistic flavor in our work. So you could create any data set you want, paradigm data set, and you can fit it into our program, and you should be able to see the results and interpret that. Another sense of extensibility is since our work, our programs are open source, like all the program code is online, you can use it for any other work to incorporate in your programs and do other things. So that's how we do our work. So as a proof, I want to show you a little program. I have 3 minutes left, I think, so I can show you a little program that I've written. All the code is in Python. All the code, some data set, everything is online already. So Google me, and you can find everything there. So, all right. So the program is here. Oops, it's dying. Never mind. It should be fine. Okay, so here is a little program with a graphical user interface, GUI. So by accessible, we mean we don't want to send you a Python script, so that, hey, here's a Python script, run it in a command line, blah, blah, blah. It's not user-friendly. So what we do is we wrote a program, very easy to use. All what you need to do is to prepare a CSV file. Use your favorite spreadsheet program, Microsoft Excel, OpenOffice, and whatnot. So now with this data set, a Spanish, so here I'm showing you a Spanish data set. So this program takes a data set like this, for example, the Spanish data set here, read the data, and then run it. And then wait for a few seconds, and something should happen. There you go. Okay. So it gives you a PDF file as the output. So if I find the Baudelaire output, so here I'm showing you the exact same thing that I showed you. So for, oops. Okay, so for Baudelaire, you can see that it's the substring approach with 3 analysis, P, E, and D, multiset approach here, and then the subsequence approach here. So I'm just showing you, I'm not lying, things are working. Oh man, my computer's not working. Let's see. So I think my computer's dying. So let me show you Arabic data quickly, and then I'll stop it. So for Arabic, we know the gold standard answer for KTB. So now I'm showing you the substring approach just doesn't work well. It just doesn't work. Okay, I hope you get the gist of my objective. So let me stop here and let people ask questions and comments. Thank you so much. Thank you. Technical issue. Sorry about that. Huh? Oh, maybe.
So you didn't show us how you actually get the vowel in the Podere case. So because of the maximal substring thing gives you the P and the D, right?
Maximal subsequence, yes.
Yeah. Right. And then there's an intuition that there's actually two versions of that with different vowels. And how do you get that?
So yes, so we won't get that when we look at paradigms one at a time, because just looking at Podere, the best that you can say is, oh, they all share P and D as a subsequence. That's the best. And we get the all-way alternation thing when we look at paradigms altogether, like a whole bunch of them, which is not the focus, which is down the road what my work will include. Yeah. So yes. So the answer is.
Is this also a claim to how ILLS works paradigm?
No pretensions to accuracy. That's a good question. I basically always get this question whether I'm modeling how, so whether it's really what happens in real world. What I want to say is we are modeling what happens in real world, but we are not sure, for example, whether it's really how the brain and so on works. So, but for sure, we are saying yes. So in a completely bottom-up empirical approach, that's how we linguists and also kids do the analysis to pick up the language. Yeah. Yes.
Your Arabic example was Romanized. Does your program only accept Romanized?
So far, yes, particularly ASCII, and that's why for Spanish, luckily the stress is not a big issue, so I just kind of took away the stress mark, which is not a big issue for me. But down the road, my program will allow Unicode input. Yes. So, yes. Yes. Right. Yes. So that's basically, it's kind of like a James question. So it's like if down the road when my program, so now it doesn't do that yet, but down the road when my program considers like paradigms altogether, then it will take care of the information, like the affixal material together. So yes, so it should. So that I completely agree with that. Yes. Mm-hmm. Yes.
So just for the Spanish case,
yeah.
The output of the test is usually PPE.
Just looking at Podere, yes, that's the answer.
So obviously, well, you guys just said the English is PPE.
Yeah, exactly.
At least it's not PPE.
Yeah.
And that resulted from inflectional stuff.
Yeah, from other paradigms, which I don't consider yet. So
that's why.
Yeah, exactly. Right. Right. Yes. So down the road, so for example, if a system considers like GOMAD as together, because GOMAD has only one single analysis, that's it. So when we put them together, we will see that for Podere, the analysis with PD is superior because the match of the affixes, because of the better match of the affixes. Does that? Oh, okay. So you're saying, can we look from the angle of affixes first, and then we all together? Right. Yes. Right. Yeah, that will be tricky. So I'll figure out how to do that in my program. Yes. Yeah. Definitely, it's worth trying. Yes, I agree. Yeah. Thank you.